Good day everyone. Today we are discussing chapter 4, The Constants of Change.
For a good many centuries, human thought about nature has swung between two opposing points of view. According to one view, the universe obeys fixed, immutable laws, and everything exists in a well-defined objective reality. The opposing view is that there is no such thing as objective reality, that all is flux, all is change. As the Greek philosopher Heraclitus put it, you can step into the same river twice. The rise of science has largely been governed by the first viewpoint. It is because increasing sign that the prevailing cultural background is starting to switch to the second way of thinking, as diverse as postmodernism, cyberpunk, and chose theory all blur the alleged objectiveness of reality and reopen the ageless debate about rigid laws and flexible change. What we really need to do is get out of this futile game altogether. We need to find a way to step back from these opposing worldviews, not so much to seek a synthesis as to see them both as two shadows of some higher order of reality. The shadows that are different only because the higher order is being seen from two different directions. But does such a higher order exist? And if so, is it accessible? Too many, especially scientist Isaac Newton, represent the triumph of rationality over mysticism. The famous economist John Maynard Keynes, in his essay Which is Newton, the title is The Man Saw Things Differently. In the 18th century and since, Newton came to be thought as the first and greatest of the modern age of scientists, a rationalist, one who taught us to think on the line of cold and untinctured reason. I do not see him in this light. I do not think that anyone who has pored over the contents of the bag which he packed up when he finally left Cambridge in 1696 and which, though partly dispersed, have come down to us, can see him like that. Newton was not the first of the age of the reason. He was the last of the magician, the last of Babylonians and Sumerians, the last great mind which looked out on the visible and intellectual world with the same eyes as those who began to build our intellectual inheritance rather less than 10,000 years ago. Isaac Newton, a posthumous child born with no father on Christmas Day with 1642, was the last wonder child to whom the Magi could do sincere and appropriate homage. Keynes was thinking of Newton's personality and of his interest in alchemy and religion as well as in mathematics and physics. In Newton's mathematics, who also find the first significant step toward a worldview that transcends and unites both rigid law and flexible flux, the universe may appear to be a storm-tossed ocean of change. But Newton and before him Galileo and Kepler, the giants upon whose shoulder he stood, realized that change obeys rules. Not only can law and flux coexist, but law generates flux. Today's emerging sciences of choice and complexity supply the missing converse. Flux generate law. But that is another story reserved for the final chapter. Prior to Newton, mathematics had offered an essentially static model of nature. There are a few exceptions, the most obvious being Ptolemy's theory of planetary motion, which reproduced the observed changes very accurately using a system of circles revolving about centers. that themselves were attached to revolving circles, wheel within wheels within wheels. But at that time, the perceived task of mathematics was to discover the catalog what we call ideal forms employed by nature. The circle was held to be the most perfect shape possible, on the basis of the democratic observation that every point on the circumference of a circle lies at the same distance from its center. Nature, the creation of higher beings, is by definition perfect, and ideal forms are mathematical perfection. So, of course, the two go together, and perfection was thought to be unblemished by change. Kepler challenged that view by finding ellipses in place of complex system of circle. Newton threw it altogether, replacing forms by the law that produced them, although its ramifications are immense. Newton's approach to motion is a simple one. It can be illustrated using the motion of projectile, such as cannonball fired from a gun at an angle. Galileo discovered experimentally that the path of such a projectile is a parabola, a curve known to the ancient Greek and related to the ellipse. So in this case, it forms an inverted V shape. The parabolic path can be most easily understood by decomposing the projectile's motion into two independent components. First is motion in a horizontal direction, and second is motion in a vertical direction. By thinking about these two types of motion separately and putting them back together only when each has been understood in its own right, so we can see why the path should be a parabola. The cannonball motion in the horizontal direction parallel to the ground is very simple. It takes place at a constant speed, as motion in the vertical direction is more interesting. It starts moving upward quite rapidly, then it is slowed down until for a split second it appears to hang stationary in the air, then it begins to drop, slowly at first but with rapidly increasing velocity. Newton's insight was that although the position of cannonball changes in quite a complex way, its velocity changes in much simpler way, and its acceleration varies in a very simple manner indeed. As you can see in figure 2, summarizes the relationship between these three functions. In the following example, suppose for the sake of illustration that initial upward velocity is 50 meters per second, then the height of the cannonball above the ground at 1 second interval is 0, 45, 80, 105, 120, 125, 120, 105, 80, 45, and 0. Figure 2. Calculus in a nutshell. Three mathematical patterns determined by a cannonball. It is height, velocity, and acceleration. The pattern of height, which is what we naturally observe, is complicated. Newton realized that the pattern of velocities is simpler, while the pattern of acceleration is simpler still. The two basic operations of calculus, differentiation and integration, let us pass from any of these patterns to any other, so we can work with the simplest, acceleration, and deduce the one who really want, or what we call height. You can see from these numbers that the ball goes up, levels of near the top, and then goes down again. But the general pattern is not entirely obvious. The difficulty was compounded in Galileo's time and indeed in Newton's, because it was hard to measure this number directly. Galileo rolled a ball up a gentle slope to slow the whole process down. The biggest problem was to measure the time accurately. The historian Stillman Drake has suggested that perhaps Galileo hummed tunes to himself and subdivided the basic beat in his head as a musician does. It is a puzzle, but the pattern of velocity is much clearer. The ball starts with an upward velocity of 50 meters per second. 1 second later, the velocity has decreased to 40 meters per second. A second after that it is 30 meters per second, then 20 meters per second, 10 meters per second, then a meter per second is stationary. A second after that is the velocity is 10 meters second downward. Using negative numbers, we can think of this as an upward velocity of negative 10 meters per second. In successive seconds, the pattern continues negative 20 meters per second, negative 30 meters per second, negative 40 meters per second, and negative 50 meters per second. At this point, the cannonball hits the ground. So the sequence of velocities measured at 1 second interval is 50, 40, 30, 20, 10, 0, negative 10, negative 20, negative 30, negative 40, and negative 50. Now that there is a pattern that can hardly be missed, but let's go one step further by looking at accelerations. The corresponding sequence for the acceleration of the cannonball, again using negative numbers to indicate downward motion, is negative 10, 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 and negative 10. I think you will agree that the pattern here is extremely simple. The ball undergoes a constant downward acceleration of 10 meters per second. The true figure is about 9.81 meters per second squared, depending on whereabouts on the earth you perform the experiment. But 10 is easier to think about. How can we explain this constant that is hiding among the dynamic variables? When all else is flux, why is the acceleration fixed? One attractive explanation has two elements. The first is that the earth must be pulling the ball downward. That is, there is a gravitational force that acts on the ball. It is reasonable to expect this force to remain the same at different heights above the ground. Indeed, we feel weight about gravity pulls our body downward, and we still weigh the same if we stand at the top of a tall building. Of course, this appeal to everyday observation does not tell us what happens if the distance becomes sufficiently large, say the distance that separates the moon from the earth. That's a different story to which we shall return shortly.
The second element of the explanation is the real breakthrough. We have a body moving under a constant downward force, and we observe that it undergoes a constant downward acceleration. Suppose, for the sake of argument, that the pull of gravity was a lot stronger, then we would expect the downward acceleration to be a lot stronger too. Without going to a heavy planet such as Jupiter, we can test this idea. But it looks reasonable, and it's equally reasonable to suppose that on Jupiter the downward acceleration would again be constant, but a different constant from what is here. The simplest theory consists with a mixture of real experiments and thought experiments is that when a force acts on a body, the body experiences an acceleration that is proportional to the force. And this is the essence of Newton's law of motion. The only missing ingredients are the assumption that this is always true, for all bodies and for all forces. Whether or not the forces remain constant, the identification of the constant of proportionality as being related to the mass of the body. To be precise, Newton's law of motion states that mass multiplied by acceleration equals force. That's it. Its great virtue is that it is valid for any system of masses and forces, including masses and forces that change over time. We could have not anticipated this universal applicability from the argument that led us to the law, but it turns out to be so. Newton stated 3 laws of motion, but the modern approach views them as the 3 aspects of a single mathematical equation. So I will use the phrase Newton's law of motion to refer to the whole package. The mountaineer's natural urge when confronted with a mountain is to climb it. The mathematician's natural urge when confronted with an equation is to solve it. But how? Given a body mass and the forces acting on it, we can easily solve this equation to get the acceleration. But this is the answer to the wrong question. Knowing that the acceleration of the cannonball is always negative 10 meters second squared doesn't tell us anything obvious about the shape of its trajectory. This is where the branch of mathematics known as calculus comes in. Indeed, it is why Newton and Leibniz invented it. Calculus provides a technique, which nowadays is called integration, that allows us to move from knowledge of acceleration at any instant to knowledge of velocity at any instant. By repeating the same trick, we can then obtain knowledge of position at any instant, and that is the answer to the right question. As I said earlier, velocity is the rate of change of position, and acceleration is the rate of change of velocity. Calculus is a mathematical scheme invented to handle questions about rates of change. In particular, it provides a technique for finding rates of change, a technique known as differentiation. Integration undoes the effect of differentiation, and integration while undoes the effect of differentiating twice. Like the twin faces of the Roman god Janus, these twin techniques of calculus point in opposite directions. Between them, they tell you that if you know any one of the functions' position, velocity or acceleration at every instant, then you can work out the other two. Newton's law of motion teaches an important lesson, namely that the root from nature's law of nature's behavior need to be direct and obvious. Between the behavior, we observe that the laws that produce it is crevasse, which the human mind can bridge only by mathematical calculations. This is not to suggest that nature is mathematics, that, as the physicist Paul Dirac put it, God is a mathematician. Maybe nature's pattern and regularities have other origins, but at the very least, mathematics is an extreme effective way for human beings to come to grips with those patterns. All of the laws of physics that were discovered by pursuing Isaac Newton's basic insight that change in nature can be described by mathematical processes. Just as form in the nature can be described by mathematical things have a similar character. The laws are formulated as equations that relate not the physical quantities of primary interest, but the rates at which those quantities change with time, or the rate at which those rates change with time. For example, the heat equation, which determines how heat flows through a conducting body, is all about the rate of change of the body's temperature, and the wave equation, which governs the motion of waves in water, air, or other materials, is about the rate of change of the rate of the height of the wave. The physical laws of light, sound, electricity, magnetism, and elastic bending of materials, the flow of fluids, and the course of a chemical reaction are all equal equations for various rates of change. Because a rate of change is about the difference between some quantity now and its value an instant into the future. Equations of these kinds are called differential equations. The term differentiation has the same origin. Ever since Newton, the strategy of mathematical physics has been to describe the universe in terms of differential equations and then solve. However, as we pursue this strategy into more sophisticated realms, the meaning of the word solve has undergone a series of major changes. Solve, originally it implies finding a precise mathematical formula that would describe what a system does at any instant of time. Newton's discovery of another important natural pattern, the law of gravitation, rested upon a solution of this kind. He began with Kepler's discovery that the planets moves in ellipses, together with two other mathematical regularities that were also noted by Kepler. Newton asked what kind of force, acting on a planet, would be needed to produce the pattern that Kepler had found. In effect, Newton was trying to work backward from behavior to laws, using a process of induction rather than deduction. And he discovered a very beautiful result. The necessary force should always point in the direction of the sun, and it should decrease with the distance from the planet of the sun to the sun. Moreover, this decrease should obey a simple mathematical law, the inverse square law. This means that the force acting on a planet at, say, twice the distance is reduced to 1/4. The force acting on a planet at 3 times the distance is reduced to 1/9, and so on. From this discovery, which was so beautiful that it surely concealed a deep truth about the world, it was a short step to the realization that it must be the sun that causes the force in the first place. The sun attracts the planet, but the attraction becomes weaker if the planet is farther away. It was a very appealing idea, and Newton took a giant intellectual leap. He assumed that the same kind of attractive force must exist between any two bodies whatsoever, anywhere in the universe. And now, having induced the law of the force, Newton could bring the argument full circle by deducting the geometry of planetary motion. He solved the equations given by his laws of motion and gravity for a system of two mutually attracting bodies that obeyed this inverse square law. In those days, solved meant finding a mathematical formula for this motion. The formula implied that they must move in ellipses about their common center of mass. As Mars moves around the Sun in a giant ellipse, the Sun moves in an ellipse so tiny that its motion goes undetected. Indeed, the Sun is so massive compared to Mars that the mutual center of mass lies beneath the Sun's surface, which explains why Kepler thought that Mars moved in an ellipse around the stationary Sun.
However, when Newton and his successors tried to build on his success by solving the equations for a system or 3 or more bodies such as Moon, Earth, Sun, or the entire solar system, they ran into technical trouble, and they could get out of trouble only by changing the meaning of the word solve. They failed to find any formulas that would solve the equations exactly, so they gave up looking for them. Instead, they tried to find ways to calculate approximate numbers. For example, around 1860, the French astronomer Charles Eugene Delaunay filled an entire book with a single approximation to the moon of the moon, as influenced by the gravitational attraction of the Earth and the Sun. It was an extremely accurate approximation, which is why it filled a book and it took him 20 years to work it out. When it was subsequently checked in 1970, using a symbolic algebra computer program, the calculation took a merely 20 hours. Only 3 mistakes were found in Delaunay's work, none serious. The motion of the Moon, Earth, and Sun system is said to be a 3-body problem for evident reasons. It is so unlike the nice, tidy 2-body problem. Newton solved that it might as well have been invented on another planet in another galaxy or in another universe. The 3-body problem asked for a solution for the equations that describe the motion of 3 masses under inverse square law gravity. Mathematicians tried to find such a solution for centuries but met with astonishingly little success beyond approximations. Despite intensive effort, more than 3 centuries after Newton, we still do not have a complete answer to the 3-body problem. However, we finally know why the problem has been so hard to crack. The 2-body problem is integrable. The laws of conservation of energy and momentum restrict solutions so much that we are forced to take a simple mathematical form in 1994. Sihong Sia of the Georgia Notice that this approach again changes the meaning of solve. First, the word meant find a formula, then its meaning changed to find approximate numbers. Finally, it has in effect become tell me what the solution look like. In place of quantitative answers, we seek qualitative ones. In a sense, what is happening looks like a retreat. If it is too hard to find a formula, then try an approximation. If approximation aren't available, try a qualitative description. But it is wrong to see this development as a retreat. For what this change of meaning has taught us is that for questions, like the three-body problem, no formulas can exist. We can prove that there are qualitative aspects to the solution that a formula cannot capture. The search for a formula in such questions was a hunt for a mare's nest. Why did people want a formula in the first place? Because in the early days of dynamics, that was the only way to work out what kind of motion would occur. Later, the same information could be deducted from approximations. Nowadays, it can be obtained from theories that deal directly and precisely with the main qualitative aspects of the motion. As we will see in the next few chapters, this move towards an explicitly qualitative theory is not a retreat but a major advance. For the first time, we are starting to understand nature's pattern in their own terms.